just want to thank everyone for coming to this talk. And I really want to thank the organizers for having this. I speak at a lot of different conferences around the country, and wherever I go, people always talk about this conference and tell me I should speak here. So I've been really looking forward to coming here. I understand why people love this conference so much. When I interact with everyone, it's more like a family, and I've never felt a conference like this before. So I really appreciate being here and really appreciate you guys coming to this talk. So we're going to talk about Swift for TensorFlow, and this talk is not what you think it is. We're going to get into that. I'm going to talk about why machine learning is so important. This is a very heavy talk. I'm going to try to explain all of machine learning in 30 minutes, which is going to be kind of painful. But I want to explain why it's so important. When the World Wide Web first started out, I kind of flew around and told everybody, this is going to make things different. You know, it's going to help us, and it's going to make things a little better for everybody. And then it turned out made things a little better for us. And then when mobile came out, I flew around the country teaching Android and iOS. And I said, look, mobile is going to make things better for people. And I love iOS, I love Android, I love teaching and working on it. And now, machine learning, right? And what I want to say is, after the web and after mobile, I really believe machine learning is the next big thing. And I had a nightmare last night that I woke up at 4 in the morning, flew down from Silicon Valley, came here, gave a horrible talk, and you guys all walked away going, machine learning sucks. Now that would be a nightmare for me, because even if this talk sucks, I want you to understand, just like the World Wide Web, just like mobile, machine learning is going to be, it has lots of amazing potentials. One of the ways I'm using it is I wrote a little app that allows people to say, I want to go see Endgame. And I want to invite people, but I don't know who to invite. I wrote a little app, and what people do is they go through and they just show what movies they like by swiping left and right. And this gives me an idea of what kind of movies people enjoy. Then what I do is I group people together. Well, the little inference engine, I group people together, and they go see the movie together, and then I find them a coffee shop that the inference engine chooses for them, and they can go and discuss the movie. Because I like to go see movies, and then I like to go talk about them. And so this little inference engine really helps us bring together the right group of people to have enough diversity in the group to have fun talking about these movies. Now, this talk is going to be a lot. I've given it a couple times before, and it's always been very difficult. And you figure I would learn, but I keep trying, and hopefully you guys don't stone me on the way out. But this is just an appetizer, right? So what I'm going to say right now is just the beginning of the conversation. I am here for 3 days, and you can come and ask me questions about how machine learning works, so I can fill in the gaps that I couldn't do in the 30-minute talk. 30 minutes talks, and then 15 minutes talking about Swift for TensorFlow. So this is just an appetizer, right? Now, my business card is sitting on the corner here. So if you like the talk or you don't like the talk, please grab one of my business cards. It has my email address, and just tell me what you think, right? Because the more feedback I get, the better the talk is going to get. So if it doesn't go well, you can vent all you want. My business card's right there. So before you leave, just grab a business card. TensorFlow for Swift is not about iOS at all. It's a whole new way of thinking about machine learning, where the compiler understands how machine learning works. So Chris Latner, I actually had him sign my laptop because I'm such a geek. I think he just did an amazing job with Swift, and now he's rewriting the compiler so it understands machine learning, which is going to propel us into a whole new age of ML. Machine learning is very easy as a concept. Right? Basically, all it is this picture up here. You take data and you ship it off to a country where people don't get very high wages, and you ask them to take that data and look for features and then put labels on those features. That will generate a model, right? And then they ship that model back to us, and we use that model to be able to do predictive analysis. So throughout this talk, you're going to be hearing me say over and over again, features, labels, models. That's all machine learning is. And we're going to be talking about supervised machine learning and how it fits into this. So a little bit about how does machine learning fit into artificial intelligence? Artificial intelligence is we're training computers to think like human beings. Machine learning is we're using algorithms and statistical models to do artificial intelligence. Deep learning is where we're using artificial neural nets to do machine learning. So deep learning uses artificial neural nets to build machine learning to help us do artificial intelligence. That's how those words all link together. Now, machine learning has come a long way. There was a movie, Star Trek, where they had a funny scene where Scotty wanted to work with the computer and he picked up the mouse and he talked to the mouse trying to get information out of the computer, and everyone thought that was very funny. But today, that really happens. I can actually talk to my computer and get information out of it because of machine learning. And not only that, but if you have an Amazon, you can actually do these different Star Trek commands to it, and it will actually respond in a very clever way. So where is machine learning used? Now, there's three ways you can program things, right? You can program things empirically where you line by line have to specify exactly what the computer has to do. You can do declarative programming where you kind of declare to the machine what you want. And that's where Swift UI comes in, because no longer do we imperatively write what every single piece of the menu has to do. We just say we want a menu system with Swift UI. And then what Swift UI does is it goes, okay, the operating system figures out what a menu is. If you're on a Mac, that's a pull down. If you're on an iPhone, that's tabs. If you're on a watch, that's the crown, right? So therefore, with declarative programming, you're kind of just declaring what you want. Machine learning is the highest level. You're not programming the computer at all. What you're doing is you're basically telling it, here are some ideas about what I want you to do, and then I'm going to negatively impact your system if you do them wrong, right? So basically, you put in data and it generates the rules. So this robot was trained to walk like a kid does, right? When a kid learns how to walk, you don't sit there and say, okay, take your next step. Okay, now lift your foot a little bit and then move it to the right. No, wave your arm. Oh, no, you're falling over. The kid just starts walking, and over time, he learns how to walk properly. And that's what the power of machine learning is, right? It's going to learn its environment by just understanding as it goes. Now, I'm not quite sure how Boston Robotics built this robot to run. They could have done some empirical programming and played with the sensors. But I guarantee you, DeepMind at Google got this machine to run without ever giving it a single instruction, right? All it did was use machine learning, and it learned how to run on its own. And it came up with some very, very clever ways of running that are probably even more efficient than human beings run. In fact, in one of the running models, it started running kind of like galloping like a horse. So machine learning is really nice because as the algorithms run through their environments, they're learning. So in a self-driving car, if it sees a tree and identifies a tree, it knows over time it learns, okay, trees don't move, human beings do move, bicycles move a little faster. All those rules that it generated, it learned itself, and we didn't have to do any programming. And that's the power of ML. Now, data is huge. We're going to be talking about supervised machine learning. And if you have bad data, you get bad results. So feature engineering is really important. You're going to spend a lot of time as an ML person actually working with your data. And sometimes when you're trying to find your features that you're going to use in your system, they don't really give you enough resolution. And you take your features and you start combining them and you make synthetic features until you get a system that works. And we're going to get deeper into this. Now, one place where you can go to get a lot of your data is Kaggle.com. And they curate data that's been already labeled by users. So what you can say is you have a whole bunch of pictures of cats and dogs. They pick the features out from the different cat and dogs, and they say, this is a cat and this is a dog. And there's 20,000 data sets up there. There's cancer diagnostic data. There is inferences for people with movies. There's clothing. I mean, almost any kind of data set you can imagine where there's some features and then you can get some categories out of them, which we are calling labels. You're going to find them up there. To make it real, let's pretend that I put these flowers all over the conference. And what I need to do is tell you, one of them is poisonous and you don't want to touch it. So what we have to do is we have to identify these flowers and make sure that we're not eating the ones that are poisonous. We want to set up the problem in the way that we can get this data into the computer. We can't just take the flower and rub it on the screen and say, okay, what kind of flower it is. We have to figure out how we're going to describe the flower to our program. And the way we do that is with our features. So here, the features we're going to choose are the widths and the lengths of the petals. And so we have 4 features up here, and our labels are the 3 different kind of flowers we're looking for. So again, features, labels. Now our data looks like this that we're going to train our model, right? Features, model, label. I'm going to be saying that over and over again. This is the data that we're going to use to train our model in our supervised learning. To read this, it has 120 pieces of information. It has 4 features and 3 labels. Now, this last column is what type of flower it is, and we see that there's 3 of them, so it's 0, 1, and 2 is how we encode it. Now, encoding is necessary because we have to be able to talk about numbers, so we encode everything. This is the second flower. No, this is the last flower, and this is the last flower. So we expect these features to be very similar. If we don't have good resolution in our features, our models are never going to work. So this is our data set. These are our widths, and these are our labels. Now, I hypothesize that I can come up with a system in which if you give me the lengths and the widths, I can put it through some sort of a system where I give you back a probability of what kind of flower it is by what features you give me. So you can give me a set of features, I'm going to run it through my model, and I'm going to tell you which label we're looking at, the probability of which one is our output. Now, the model that I'm going to propose is going to have these nodes in it, and these are layers, and each layer has computational nodes. And inside of each of these nodes, we're going to have a weight and a bias, in that if you give me a certain width and a length, when I multiply it and bias it, it's going to give me a system of equations that as I run through this, I'm going to get the right probability out. This is what I'm hypothesizing. This is how we're going to build our system. Now, there's 3 ways to solve a problem. All problems are solved only 3 ways. You can do it in math with equations. You can do a transform. You can do a Laplace transform or a Fourier transform. Take it into one domain, solve it, and then bring it back. Or a lot of times, the way we solve problems is we just kind of guess at them. Let's just try this. How bad did that work? Well, it worked this bad. Okay, then try this one. And that's kind of how supervised machine learning works. We know that these are the answers we want, and this is where our prediction is, and this is the error, right? So if I was to move my prediction closer to my answers, my loss function will be better. So this is my first guess, this is my second guess, and this is my last guess, where the errors decrease as I move my prediction. We're going to come later in the talk, and we're going to talk about how you make that movement, and that movement is done by gradient loss. I keep talking about supervised learning, and supervised learning is where you have 2 data sets. You have your input-output pairs. So you know that when you're putting your inputs in, what the outputs should be. So this is an example of how it works. We have our features, our widths and our lengths, and we make a prediction, and then we look at our label. Which flower did it say it was? We know what flower it should have been by the by the widths and the lengths we put in. So we know how far we are from the right answer. We make another prediction, and we go through this loop until we train our model properly. Graphically, what's actually happening is this is our loss curve. Down here, we're making perfect predictions, and up here, we're making horrible predictions. All of our weights and all of our guesses are along this curve. Now, if we're sitting here at this point and we want to make our next guess, what we can do is we can find the derivative of that point, because the derivative of that point will give us the slope of the tangential line, right? So if we look at that point and we calculate the derivative of that point, then we get the slope of the tangential line, and you can call the gradient, the negative gradient, it points down to make the error function less. So this tells us which way we need to move our computations to be able to lessen our losses, right? So if we move to the next point, and again, we calculate the derivative at that point, we're going to get the slope to the tangential line. It's going to be pointing down the loss function. And if we did that one more time, right, if we calculate the derivative of this point, it would be a constant, which means you're either at a local minima or a local maxima. And this is the perfect place for our model to be able to make predictions. If we go too far, we notice that it flips direction, right? So the derivative of this point, the slope points in the opposite direction. We know that we went too far. When we're training our system, what happens is if we walk too slowly down this line, it'll take forever to get to this point. If we go too fast, we hop back between these 2 points, right? And that's called our training rate. So if our training rate is really, really slow, we don't go anywhere. If our training rate is too high, we bounce back and forth. And I visualize this in the next graph here. So our loss goes extremely high if our training rate is very high. It doesn't go anywhere if our training rate is too low. And if we have a good training rate, then we're going to really nicely calculate our derivatives and get our slopes and walk slowly down. Now, how do we get our model built? Our model is going to be built with layers of neural nets, where we're going to be putting in inputs. It's going to go through the neural net, and it's going to generate our labels. This is a graphical representation. Say I would like to know if I'm holding an apple. Anytime I have something that's red in a circle, I'm going to call it an apple. So basically, I'm going to quantify all my colors. Say red is 7, and a shape of, I have all these different shapes. I quantify them to numbers also, and if I have a shape of 7, that's a circle. So if I put a 7 and a 7 in here, I have these computational nodes in here that have a weight and a bias that are generating equations for me in such a way that if I have a 7 and a 7 in here, I get a 1 here, which means you have an apple. If I put in any other numbers in here, these weights and biases will generate a series of equations that will give me a 0 in here. That's how I propose we're going to build our model. And as we get further deep into it, I'm going to explain how this works. So, some machine learning terms. The features are the inputs. The labels are what we're categorizing. Our layers are made out of nodes. Our nodes are the computational units that have weights and biases in them. When we're training it, that's called our training. Once we've trained it and we want to use it, that's called our inference. We have a regression model, which is a continuous value. If I ask you how much did you like that movie, that is a regressive model. If I ask you, did you like that movie, yes or no, that is a classification model. So those are the two differences. Now, I want to make one thing, I want to visualize one thing in your head, which is called backpropagation. Say we want to know if we have a cat or a dog. When we put in the size of the eyes and the size of the tail and we put in the size of the body, we're going to put those features in, and we're going to have these weights and biases in these nodes that are going to take these lengths, and they're going to calculate numbers, and as they calculate numbers, they're going to come out here with 2 predictions. If we put in the numbers for a cat and it comes up for a dog, what we're going to do is we're going to go back and reset those weights and balances so that this actually comes out to be a dog. So if we have a cat here and it says it's a dog, again, we're going to go back and we're going to redo the weights and biases in here so that the system, when we put in our correct features, we're getting the correct labels. And that training is done through backpropagation. Now, the neural net is made out of nodes. The nodes have weights and biases that are doing computations to be able to get us to our probabilities. One way you can think about this is when I do a handwritten number, I'm going to have those pixels. Now I'm going to take all those pixels and I'm going to take that 28 by 28 pixel grid. I'm going to string it all out. This is really bad because now I've lost my shape of my number. But let's just work with this. We're going to take these blocks and when, depending on which ones are lit and not lit, we're going to put it through a set of weights and biases in such a way that these weights and biases are only going to light up if these pixels are an 8. And if I put in a 4, it's only going to light up a 4. And what we do is we take these weights and biases and we put them through something that's called a soft max. And the soft max is going to take all our crazy numbers and reduce it to just something that is between a 0 and a 1. And we're going to get a little deeper into that in a second. But I wanted you to visualize what it looks like in the computational nodes. This is the equations that the computational nodes are going to generate. So we have a handwritten 4 here, and these are the pixels that get lit up when you do a handwritten 4. And these are also the pixels that get written up for another handwritten 4. These sets of features should be very similar, or else it's going to be really hard for us to tell our 4s apart. Now we take these pixels and we multiply them by our weights, and we add our biases, and we get our labels. And we do this for all the sets of pixels we have, to all the sets of weights that we have, to all the biases we have to get our labels. I just want you to visualize what all those equations look like when we're looking at our hidden layers. Now, when we're going through our hidden layers, we could have lots of diverse numbers coming through. And we don't want our numbers to get into the stratosphere. So every time they go through our layers, we're going to give it an activation function. The activation function can take any number from 0 to 5 trillion, and it's going to normalize it from 0 to 1. So this sinusoidal, no matter what number you give it, it's going to renormalize it between 0 and 1. That means no matter how many layers of neural nets we have, hidden layers we have, we're only going to output something between 0 and 1. And this is going to make our last layer very easy. No matter how much input we give it, we know our last layer is just going to be a sum of numbers between 0 and 1. And that's why we have to have the activation. Now, no one uses that sinusoidal. We all use this Raoul function. It works much better. So again, let's visualize how this works. We have our weights, and we multiply it by our input. We add our bias. We put it through our activation energy here, and then we put it through softmax, and softmax gives us the probability of what this number could possibly be. Now, we call it softmax because what softmax is doing, it's taking things that are large and making them a lot larger. And it's taking things that are small and just knocking them down a little bit. So it is a max function, but it's a softmax function. And the softmax is our last layer, and it allows us to get our probability of what our label is. We need to know how good our predictions are. So once we come out of our softmax, we have these probabilities. But while we're doing supervised machine learning, we know what the answer was supposed to be, and this is the distance between what the probabilities were and what we expected. This distance, you could just subtract them. You could just subtract these and say, this is our loss. But actually, this cross-entropy function works a lot better. You take these actual values, and then you take the logs of the computed probabilities out of softmax. You take the dot product of them, and that's how we're going to compute our loss when we do our supervised learning. So again, our loss function, our entropy loss function is how well we're doing between our training set and our validation set. And accuracy is how well we're doing after we train our models. So when you go in for your machine learning interview, right, they're going to talk about features, they're going to talk about labels, they're going to talk about softmax, they're going to talk about entropy loss functions and accuracy. Entropy loss function is how well we're doing while we're doing our training, and accuracy is how well we're doing after our training. So we have our training time and we have our test time. We take our data and we start using it to train our neural net. And we notice that we're doing very, very good while we're training it. But then when we go to actually test it with new data, we're doing really bad. And that's just because we overtrained the model. And we can realize we overtrained the model because it's doing really well on our training loss and it's doing really bad on our test loss. The way we get around that is we take our full data and we break it into our test and our training. So when we start, we're going to take and we're going to do a whole bunch of training. We're going to get that model, and that's going to be fully trained. We're going to take that inference model and we're going to show it to data that it's never seen before. This is our validation set, and we see how we do on that error. And if we're doing the same, then we're very happy. And we keep going through this cycle until our training set is doing as well as our validation set. And then we show it a last set of data that it's never seen before, and that's the test set. So usually you take your data and you break it into 3 pieces. You train with a piece until your error loss is very low. And then you show it your validation data. And then the error could be very high. You go back to a training model and you keep doing that. And pretty soon your validation set and your training set have both low functions, and then you show your last test set that it's never seen before, and that should also be doing well. So when people are talking about their validation set or their test set or their training set, this is the context in which they're talking. Now, if the system is overtrained, what you can do is you can set a dropout rate. At this point, some of the nodes inside the neural net, you stochastically decide to drop them out. And that forces the system to have redundancy in the other nodes. And this helps when you're overtraining your model. What happens when you're overtraining the model, it's basically memorized the data set, and it's not actually doing machine learning. So you have to compensate for that. And one of the ways you compensate for that is you set a dropout rate. The other way is you do batch normalization. And batch normalization gives you one set of equations before your weights and biases. Now, if your system needs it, it'll use it. It's this alpha x plus beta. If your system doesn't need it, it'll set alpha to 1 and beta to 0, and the normalization never happens. But if it does need it, the normalization sits right in front of the activation fit, and it allows the system to use this biasing to fix if it's being overtrained. So that's batch normalization. People spend a long time, much longer explaining it, but I just wanted you to hear the term. Now, at this point, normally we would be completely done, and we would go and train models. But because TensorFlow, Swift or TensorFlow, actually allows you to play with the actual machine learning model, we have to go deeper and actually understand how do models learn. Here, what you see is in a tensor, when we train it, we just use this thing called gradient descent. We give it our learning rate and our cross-entropy loss function, and TensorFlow takes care of everything. But Swift or TensorFlow actually wants to give you an opportunity to understand and play with this gradient descent optimizer. Now, the gradient descent optimizer works like this. This is the total solution space of our model. If you plugged in every weight and bias, you would get this solution space. And then this is the error loss. So right here at the bottom of the space, it's making perfect predictions. We want to move from the top to the bottom. And remember what I was saying about the tangent to the line points to the gradient? Well, that's exactly the same thing that's happening here. By using partial differential equations, we're going to figure out where the gradients are along this line, and we're going to move down them. Now, sometimes you have hundreds of thousands of variables you have to deal with, so you can't find the partial differential equation of all those variables. So what you do is you do a stochastic gradient descent. You choose only a small set of your variables, and you find those gradients, and you walk down that. And the way it works is partial differential equations allow you to find the slope of each individual variable one at a time, and then you can add all those gradients together, and it'll tell you the total gradient you should walk. So the first thing you do is you find the gradient for the x, and it points one way, and then you find the y, and it points kind of like the similar way, and then the z. Add all those vectors together, and that's the total gradient that you want to walk down to change your biases and your weights to lower your error function. So partial differential equations is very important to machine learning. It's how we know which way to move our weights and biases to lower our error. Nancy has an amazing video that explains partial differential equations, so I'll let that to her. But here's a visualization of some optimizers, and what they're doing is they're calculating the partial differential equations across various variables and then updating their weights and biases and walking down the gradient. Now, you can't just say, hey, computer, solve this partial differential equation for me, right? It has to somehow be able to calculate that. We do it in school numerically, right? You could do it with symbolics. But none of that's going to work for the computer. The computer has to do it with automatic differentiation, which uses the chain rule. So automatic differentiation is how computers solve the gradients. Automatic differentiation is using partial differential equations to figure out the gradients so that you can update your weights and biases to get lower loss functions. People confuse automatic differentiation with the backpropagation. Backpropagation is the process by which you reset your weights and biases to get the right answer. Automatic differentiation is using the chain rule to figure out how to change those weights and biases to be able to lower the error function. That's how those two are related. Now, here's another real nice video that explains how the chain rule works. But basically what the chain rule does is it breaks up the computation to smaller pieces, lots and lots of smaller pieces. So here, when you're working with TensorFlow, it generates the forward pass here. So you can see here's our input and our weights. They're multiplied. They're added to our bias. They go through our activation energy, through through batch normalization. They're added, and this is the components of the chain rule that allow you to build this. TensorFlow gives you the derivatives of all that so that it can figure out how to change the weights and biases. So when you write TensorFlow code, when that tensor runs, it's not running your code anymore. It's running a graph representation of the calculations you put into it. So this runs in memory. And people in TensorFlow love this because you can take this stuff and you can move it to GPUs and CPUs and all this other stuff, right? That's great, but you can't put a breakpoint in this. You can't walk through this because your code is gone. Your code is gone, and now the chain rules have generated this graph, and this graph is running in the cloud on TPUs, CPUs, GPUs. TPUs are tensor compute units. So this becomes a huge problem to debug this. How do you set a breakpoint? Well, Swift for TensorFlow, because the compiler understands how this graph is generated, you can actually walk through this code. Now, Swift for TensorFlow is only at 0.3, right? It's just like barely started being worked on. TensorFlow, Google's machine learning algorithm, is on 2.0, and it actually can do eager execution. That means even knowing it generates that graph in the cloud, you are able to step through your code. This was just released under TensorFlow 2.0. So again, TensorFlow is from Google. It's second rev. Swift for TensorFlow is in research, and it's in 0.3. So TensorFlow 2.0 can do eager execution, but it also has estimators. These estimators can do the training, evaluation, prediction, and exporting of the model, all with an estimator. So what you do is you take your data and you give it to an estimator, and the estimator gives you a model, you put your model on your phone, and you're done. So TensorFlow has come a long ways. Now I just want to show you really quick, this is what an actual inference engine looks like. you have a whole bunch of features coming in from different sets, and then you go through your softmax, but your softmax could actually be several different neural nets combined. Very complex. When you're building your neural net, these are the parameters you're going to be setting. You're going to be setting your learning rate, how many times you're going through the neural net, your batch size for your input, your activation function is almost always the rule. You have your hidden layers, your weights, and your dropout rate. TensorFlow has a online tool that you can use to actually visualize this. Here you put in your features, your hidden nodes are being built here, and then this is the data that's coming out. And so if we take these features and we want to match this pattern, you can actually see the features being added to the weights and biases, and the size of these is how big the weight is, and you can see that it's generating this pattern. Here's the test loss, and here's the training loss of this neural net running, and this all runs in the browser. It's called TensorFlow Playground, and you guys should all go play with it to really get a deeper understanding. Now, remember before I said that a convolutional neural net so before when we were doing numbers, we just had a string of bits, but we lost shape information. A convolutional neural net will actually keep the shape information for you. And what that allows you to do is, instead of taking the bits and stringing them out, we're going to have groups of pixels that we're going to make the neural nets from. So instead of a string, we're going to pool things. And here, this is how convolutional neural nets work, right? So you have a convolutional layer, and you read this. We have a 5 by 5, one channel. We're going to go to four layers. So then we go 4 by 4, 4 layers to 8 layers. Then we go 4 by 4. We read in these 8 layers. We go to 12 layers, and then we go to 17 by 17 from the 12 layers to a fully connected layer. And dependent on how you generate these convolutional neural nets, it tells you how well it's going to do generating these shapes. So you also have pooling, and between your convolutional layers and your pooling layers, depending on how you do these shapes, it tells you how well your neural net does. Now, that's great for images, but we also want to be able to do natural language processing. So for natural language processing, you use this gated redundant unit. And you put these together and you get long short-term memory. Because if you took the T, the H, and the E and you put it to a convolutional neural net, it'll tell you those are T and H and E. But what we need is to see the word the, brown, fox. And what happens now is we want to batch these words in. And these gated units now have a state, and they keep track of these state, and this is how you're able to teach text. And you can do inferences like, this movie is not good. When you put this into an RNN, it can tell you the sentiment, because the word's not is there, they didn't like it. And then you can get even fancier where you can use a CNN and an RNN, and you can actually read pictures. Now, you can take this model and you can put it into your core ML, right? So you export it. But TensorFlow for Swift is even better than all that, because in the core language, you have auto differentiation. You could actually run your code line by line, because the graph and the code are all understood by the compiler, and it can work with Python and a lot of different languages. So it's built on TensorFlow, so it has all of the nice APIs Tensor has, but it's done for Swift. And it's meant for every developer can benefit from machine learning, every application can benefit, and every platform can benefit. And the beautiful thing about Swift for TensorFlow is that you're working in Swift. Your model is in Swift, your labels are in Swift, everything you're building is in Swift. And the APIs are actually very easy to work with. So before I was talking about building a convolutional neural net. When you're working with Swift for TensorFlow, you can actually just see exactly how the convolutions are built. The pool size is put together. And when you go to train it, you can, the compiler actually understands how something is differentiable, so it can get the gradient and it knows how to update the weights and biases. And when you go to train it, we use a stochastic gradient descent, and it's just a for loop, right? And we use our soft cross-entropy function. So the APIs for Swift or TensorFlow are cutting edge. They're much better than they are for TensorFlow or any other language. And they're still evolving. So as time goes on, the way that you work with the TensorFlow ecosystem is going to get better, and it's going to just make a lot more sense. Not only does Swift for TensorFlow give you an ability to work naturally with language, but it also allows you to run your tensors in collabs, in playgrounds, and various different places. So it's really nice. This link will actually take you to a site that will allow you to run your TensorFlow in the browser, and it gives you GPUs in the cloud to use. So Swift and Collabs, it gives you semantic code completion, free GPUs, and the Swift package manager to do your learning. And because we're using Swift, and Swift, the LLVM understands C, C++, we can also speak Python. And so we have access to NumPy, which is a scientific numerical package, and Pandas, which is for data analysis. In the Swift code, we can just say we want to use Python, and it's very intuitive, and it works just like you would expect Python to work inside of normally work for you. And because we did nothing special to bring in Python, it's just called python.swift, and we bring all the Python goodness into the Swift for TensorFlow. We could do the same thing for JavaScript and Ruby. So it'd be like ruby.swift and javascript.swift. Our models could actually start using different languages. So Swift for TensorFlow works seamlessly without any wrappers with Python and C and other languages that we're going to bring in. Now, one of the most beautiful things about the Swift for TensorFlow is that the compiler understands differential programming. So anytime I want, I can say, give me a gradient of any function, and it will generate the chain rule for that, so I can get the gradient function and know how to change my weights and biases to lower my loss function. Any function I want, I can just add the word differentiable to it, and it will be able to be differentiable. And this is amazing for people who are doing ML research, because when you work with TensorFlow now, this is all hidden from you. The TensorFlow system builds that graph, and it does all the differentiation. But when you work with Swift for TensorFlow, you get to go inside that and actually play with the differentiable code. It's very easy to use. You just give it the function, the function with the tensors, and just say gradient of, and it'll give you the differential function. So differential programming, it's a new era of programming where we have the language and the compile time errors all built into the language for us to find our gradient descents. We can do eager execution, which means that the compiler understands how the graph is put together. It gives you the best of both worlds. You get a computational graph that you can run on CPUs and GPUs, but you can also step through the code. Because the compiler statically analyzes your code, it's able to generate both the graph and the runtime for you. And that is why they chose Swift for TensorFlow, because the compiler and the work that Chris Slatner's doing is allowing people to build one system. And the one system allows you to write your model in Swift, write all your algorithms in Swift, keep the entire workflow in Swift, and that way you don't have to mix and match while you're trying to do your machine learning. And you can actually set breakpoints inside your code, and the LLVM understands the graph, it understands the model, it understands the differentials. This is mind-blowing for ML people. It's just absolutely wonderful. When the AlphaGo team had to build their machine learning, they had to work with 3 different technologies. They had to work with deep learning technologies. They had to work with C++ code that had Monte Carlo algorithms in it. And then they had to build something that would run on TPUs. But Swift for TensorFlow brings all that together. All of those things are done in Swift, so it makes it infinitely much easier for you to be able to work with the system. Swift is just syntactic sugar on top of LLVM, the tensor type is just syntax sugar in front of TensorFlow, and the pi value is just syntax sugar in front, on top of pi object. That means you are actually working very close to the technologies that are necessary to do machine learning. It's just normal programming, so it works with Xcode. You can move it to anywhere you're running your Swift code. Your ML code will work seamlessly in that area, right? So it bridges the gap between what we do with what we do in machine learning and what we do normally. So okay. So basically, there's a course on how to learn how to do machine learning with Swift. It's very intensive, and it goes into much better detail about why Swift for TensorFlow is absolutely amazing. You can go to this website and run all of the features, and I really, really encourage you guys to go and learn about Swift for TensorFlow. It's the future of ML. I'm going to be around to answer any of your questions, and I apologize for trying to show you all machine learning in 30 minutes. Thanks, you guys.